In probability theory and statistics, the Poisson distribution, named after French mathematician Siméon Denis Poisson, is a discrete probability distribution that expresses the probability of a given number of events occurring in a fixed interval of time and/or space if these events occur with a known average rate and independently of the time since the last event. The Poisson distribution can also be used for the number of events in other specified intervals such as distance, area or volume. For instance, suppose someone typically gets 4 pieces of mail per day on average. There will be, however, a certain spread, sometimes a little more, sometimes a little fewer, once in a while nothing at all. Given only the average rate, for a certain period of observation, and assuming that the process, or mix of processes, that produces the event flow is essentially random, the Poisson distribution specifies how likely it is that the count will be 3, or 5, or 10, or any other number, during one period of observation. That is, it predicts the degree of spread around a known average rate of occurrence. The derivation of the Poisson distribution section shows the relation with a formal definition. History: the distribution was first introduced by Siméon Denis Poisson and published, together with his probability theory, in 1837 in his work Recherches sur la probabilité copyright des jugements en matière criminelle et en matière civile. The work theorized about the number of wrongful convictions in a given country by focusing on certain random variables and that count, among other things, the number of discrete occurrences that take place during a time interval of given length. The result had been given previously by Abraham de Moivre in De Mentura Sortisser. De probabilitate eventuum in ludus a casu fortuito pendentibus in Philosophical Transactions of the Royal Society, pa 219. A practical application of this distribution was made by Ladislaus Bortkiewicz in 1898 when he was given the task of investigating the number of soldiers in the Prussian army killed accidentally by horse kicks. This experiment introduced the Poisson distribution to the field of reliability engineering. Definition: a discrete random variable ℤ is said to have a Poisson distribution with parameter I0, if, for k equals 0, 1, 2, €, the probability mass function of ℤ is given by where E is Euler's number, k is the factorial of k. The positive real number I is equal to the expected value of x and also to its variance. The Poisson distribution can be applied to systems with a large number of possible events, each of which is rare. How many such events will occur during a fixed time interval? Under the right circumstances, this is a random number with a Poisson distribution. Properties: mean, the expected value of a Poisson distributed random variable is equal to I, and so is its variance. The coefficient of variation is, while the index of dispersion is 1. The mean deviation about the mean is. The mode of a Poisson distributed random variable with non-integer I is equal to, which is the largest integer less than or equal to I. This is also written as floor, I. When I is a positive integer, the modes are I, and IAAA1. All of the cumulants of the Poisson distribution are equal to the expected value I. The nth factorial moment of the Poisson distribution is In. Median, bounds for the median of the distribution are known and are sharp. Higher moments, the higher moments mk of the Poisson distribution about the origin are two-card polynomials in I, where the braces denote Stirling numbers of the second kind. The coefficients of the polynomials have a combinatorial meaning. In fact, when the expected value of the Poisson distribution is 1, then Dubinsky's formula says that the nth moment equals the number of partitions of a set of size n. Sums of Poisson distributed random variables, if are independent, and, then. A converse is Rayleigh-Cobb's theorem, which says that if the sum of two independent random variables is Poisson distributed, then so is each of those two independent random variables. Other properties: the Poisson distributions are infinitely divisible probability distributions. The directed Kullbacher Euro-Leibler divergence of Poisson, I0, from Poisson, I is given by. Bounds for the tail probabilities of a Poisson random variable can be derived using a Cherenkov bound argument. Recurrence relation. Related distributions, if and are independent, then the difference follows a Anscombe distribution. If and are independent, then the distribution of conditional on is a binomial distribution. Specifically, given. More generally, if x1, x2, xn are independent Poisson random variables with parameters i1, i2, in. Given. In fact, if and the distribution of conditional on x equals k is a binomial distribution, then the distribution of y follows a Poisson distribution. In fact, if conditional on x equals k follows a multinomial distribution, then each follows an independent Poisson distribution. The Poisson distribution can be derived as a limiting case to the binomial distribution as the number of trials goes to infinity and the expected number of successes remains fixed. See law of rare events below. Therefore it can be used as an approximation of the binomial distribution if n is sufficiently large and p is sufficiently small. There is a rule of thumb stating that the Poisson distribution is a good approximation of the binomial distribution if n is at least 20 and p is smaller than or equal to 0.05, and an excellent approximation if n a per mil 100 yen and np a per mil 10 currency. The Poisson distribution is a special case of generalized stuttering Poisson distribution with only a parameter. The stuttering Poisson distribution can be deduced from the limiting distribution of univariate multinomial distribution. It is also a special case of a compound Poisson distribution. For sufficiently large values of I, the normal distribution with mean I, and variance I is an excellent approximation to the Poisson distribution. If I is greater than about 10, then the normal distribution is a good approximation if an appropriate continuity correction is performed, that is, p, za per mil x, where x is a non-negative integer, is replaced by p, za per mil za plus a 0.5. Variance stabilizing transformation: when a variable is Poisson distributed, its square root is approximately normally distributed with expected value of about and variance of about 1/4. Under this transformation, the convergence to normality is far faster than the untransformed variable. Other, slightly more complicated, variance stabilizing transformations are available, one of which is Anscombe Transform. See data transformation for more general uses of transformations. If for every t greater than 0 the number of arrivals in the time interval, 0, t, follows the Poisson distribution with mean it, then the sequence of inter-arrival times are independent and identically distributed exponential random variables having mean 1/i. The cumulative distribution functions of the Poisson and chi-squared distributions are related in the following ways. And occurrence, applications of the Poisson distribution can be found in many fields related to counting, telecommunication example, telephone calls arriving in a system. Astronomy example, photons arriving at a telescope. Biology example, the number of mutations on a strand of DNA per unit length. Management example, customers arriving at a counter or call center. Civil engineering example, cars arriving at a traffic light. Finance and insurance example, number of losses claims occurring in a given period of time. Earthquake seismology example, an asymptotic Poisson model of seismic risk for large earthquakes. Radioactivity example, decay of a radioactive nucleus. The Poisson distribution arises in connection with Poisson processes. It applies to various phenomena of discrete properties whenever the probability of the phenomenon happening is constant in time or space. Examples of events that may be modeled as a Poisson distribution include the number of soldiers killed by horse kicks each year in each corps in the Prussian cavalry. This example was made famous by a book of Ladislaus Józefowicz Bortkiewicz. The number of yeast cells used when brewing Guinness beer. This example was made famous by William Seeley Gossett. The number of phone calls arriving at a call center within a minute. This example was made famous by A.K. Lang. Internet traffic. The number of goals in sports involving two competing teams. The number of deaths per year in a given age group. The number of jumps in a stock price in a given time interval. Under an assumption of homogeneity, the number of times a web server is accessed per minute. The number of mutations in a given stretch of DNA after a certain amount of radiation. The proportion of cells that will be infected at a given multiplicity of infection. The arrival of photons on a pixel circuit at a given illumination and over a given time period. The targeting of V-1 flying bombs on London during World War II. Gallagher in 1976 showed that the counts of prime numbers in short intervals obey a Poisson distribution provided a certain version of an unproved conjecture of Hardy and Littlewood is true. Derivation of Poisson distribution the law of rare events. The rate of an event is related to the probability of an event occurring in some small subinterval. In the case of Poisson distribution, one assumes that there exists a small enough subinterval for which the probability of an event occurring twice is negligible. With this assumption one can derive the Poisson distribution from the binomial one, given only the information of expected number of total events in the whole interval. Indeed, let this total number be. Divide the whole interval into subintervals of equal size, such that this means that the expected number of events in an interval for each is equal to. Now we assume that the occurrence of an event in the whole interval can be seen as a Bernoulli trial, where the trial corresponds to looking whether an event happens at the subinterval with probability. Indeed, the expected number of total events in such trials would be the expected number of total events in the whole interval. Hence, for each subdivision of the interval we have approximated the occurrence of the event as a Bernoulli process of the form. As we have noted before, we want to consider only very small subintervals. Therefore we take the limit as goes to infinity. In this case the binomial distribution converges to what is known as the Poisson distribution by the Poisson limit theorem. In several of the above examples such as, the number of mutations in a given sequence of the events being counted are actually the outcomes of discrete trials, and would more precisely be modeled using the binomial distribution, that is. In such cases n is very large and p is very small. Then the distribution may be approximated by the less cumbersome Poisson distribution. This approximation is sometimes known as the law of rare events, since each of the n individual Bernoulli events rarely occurs. The name may be misleading because the total count of success events in a Poisson process need not be rare if the parameter np is not small. For example, the number of telephone calls to a busy switchboard in 1 hour follows a Poisson distribution with the events appearing frequent to the operator, but they are rare from the point of view of the average member of the population who is very unlikely to make a call to that switchboard in that hour. The word law is sometimes used as a synonym of probability distribution, and convergence in law means convergence in distribution. Accordingly, the Poisson distribution is sometimes called the law of small numbers because it is the probability distribution of the number of occurrences of an event that happens rarely but has very many opportunities to happen. The Law of Small Numbers is a book by Ladislaus Bortkiewicz about the Poisson distribution, published in 1898. Some have suggested that the Poisson distribution should have been called the Bortkiewicz distribution. Multidimensional Poisson process. The Poisson distribution arises as the distribution of counts of occurrences of events in intervals in multidimensional Poisson processes in a directly equivalent way to the result for unidimensional processes. Thus, if D is any region the multidimensional space for which D, the area or volume of the region, is finite, and if n, D, is count of the number of events in D, then other applications in science, in a Poisson process, the number of observed occurrences fluctuates about its mean I with a standard deviation. These fluctuations are denoted as Poisson noise or as shot noise. The correlation of the mean and standard deviation in counting independent discrete occurrences is useful scientifically. By monitoring how the fluctuations vary with the mean signal, one can estimate the contribution of a single occurrence, even if that contribution is too small to be detected directly. For example, the charge E on an electron can be estimated by correlating the magnitude of an electric current with its shot noise. If n electrons pass a point in a given time t on the average, the mean current is. Since the current fluctuations should be of the order, the charge can be estimated from the ratio. An everyday example is the graininess that appears as photographs are enlarged. The graininess is due to Poisson fluctuations in the number of reduced silver grains, not to the individual grains themselves. By correlating the graininess with the degree of enlargement, one can estimate the contribution of an individual grain. Many other molecular applications of Poisson noise have been developed, for example, estimating the number density of receptor molecules in a cell membrane. In causal set theory, the discrete elements of spacetime follow a Poisson distribution in the volume. Generating Poisson distributed random variables, a simple algorithm to generate random Poisson distributed numbers has been given by Muth. Algorithm Poisson random number, init, let LAAI, KA0 and PA1. Do, KAK plus 1. Generate uniform random number UN, 0, 1, and let PA U. While P, L. Return KA1. While simple, the complexity is linear in the returned value K, which is I on average. There are many other algorithms to overcome this. Some are given in R and some data, see references below. Also, for large values of I, there may be numerical stability issues because of the term I. One solution for large values of I is rejection sampling, another is to use a Gaussian approximation to the Poisson. Inverse transform sampling is simple and efficient for small values of I, and requires only one uniform random number U per sample. Cumulative probabilities are examined in turn until one exceeds U. Parameter estimation, maximum likelihood, given a sample of n measured values key equals 0, 1, 2. I equals 1. N, we wish to estimate the value of the parameter I of the Poisson population from which the sample was drawn. The maximum likelihood estimate is. Since each observation has expectation I, so does the sample mean. Therefore the maximum likelihood estimate is an unbiased estimator of I. It is also an efficient estimator, that is, its estimation variance achieves the Kramer copyright Ra lower bound. Hence it is MVUE. Also it can be proved that the sum is a complete and sufficient statistic for I. To prove sufficiency we may use the Factorization Theorem. Consider partitioning the probability mass function of the joint Poisson distribution for the sample into two parts, one that depends solely on the sample and one that depends on the parameter and a sample only through the function. Then is a sufficient statistic for. Note that the first term depends only on. The second term depends on the sample only through. Thus, is sufficient. For completeness, a family of distributions is said to be complete if and only if implies that for all. If the individual are I-id, then. Knowing the distribution we want to investigate, it is easy to see that the statistic is complete. For this equality to hold, it is obvious that must be 0. This follows from the fact that none of the other terms will be 0 for all in the sum and for all possible values of. Hence, for all implies that, and the statistic has been shown to be complete. Confidence interval. The confidence interval for the mean of a Poisson distribution can be expressed using the relationship between the cumulative distribution functions of the Poisson and chi-squared distributions. The chi-squared distribution is itself closely related to the gamma distribution, and this leads to an alternative expression. Given an observation K from a Poisson distribution with mean I1/4, a confidence interval for I1/4 with confidence level 1 I plus or minus is. Or equivalently. Where is the quantile function of the chi-squared distribution with n degrees of freedom and is the quantile function of a gamma distribution with shape parameter n and scale parameter 1. This interval is exact in the sense that its coverage probability is never less than the nominal 1 I plus or minus. When quantiles of the gamma distribution are not available, an accurate approximation to this exact interval has been proposed. Where denotes the standard normal deviate with upper tail area I plus or minus /2. For application of these formulae in the same context as above, one would set. Calculate an interval for I1/4 equals ni, and then derive the interval for I. Bayesian inference. In Bayesian inference, the conjugate prior for the rate parameter I of the Poisson distribution is the gamma distribution. Let denote that I is distributed according to the gamma density G parameterized in terms of a shape parameter I plus or minus and an inverse scale parameter I squared. Then, given the same sample of n measured values key as before, and a prior of gamma, I plus or minus, I squared, the posterior distribution is. The posterior mean E, I approaches the maximum likelihood estimate in the limit as. The posterior predictive distribution for a single additional observation is a negative binomial distribution, sometimes called a gamma-Poisson distribution. Simultaneous estimation of multiple Poisson means, suppose is a set of independent random variables from a set of Poisson distributions, each with a parameter, and we would like to estimate these parameters. Then, Clevenson and Zeidke show that under the normalized squared error loss, when, then, similar as in Stein's famous example for the normal means, the MLE estimator is inadmissible. In this case, a family of minimax estimators is given for any and as. Bivariate Poisson distribution, this distribution has been extended to the bivariate case. The generating function for this distribution is with. The marginal distributions are Poisson, I1, and Poisson, I2, and the correlation coefficient is limited to the range. A simple way to generate a bivariate Poisson distribution is to take three independent Poisson distributions with means and then set. The probability function of the bivariate Poisson distribution is. See also. Notes. References: Joachim H. Ahrens, Ulrich Dieter. Computer methods for sampling from gamma, beta, Poisson and binomial distributions. Computing 12, 223 246 doi, 10.1007/BF02293108. Joachim H. Ahrens, Ulrich Dieter. Computer generation of Poisson deviates. ACM transactions on mathematical software 8, 163 179 doi, 10.1145/355,993.3559997. Ronald J. Evans, J. Boersma, N. M. Blackman, A. A. Jaggers. The entropy of a Poisson distribution, Problem 87-6. Siam Review 30, 314 317 doi, 10.1137/1030059. Donald E. Muth. Semi-numerical algorithms. The Art of Computer Programming, Volume 2. Addison Wesley A.